All right, so we're talking about filament selection for aircraft. There's a chart behind me, and I'm not going to go into a lot of details. I'm going to use this as a reference, but this is on Bamboo Labs filament comparison chart, so that you can look at the parameters of all the filaments. So, but let's talk about decision points, and this is important because these are decision points that you wouldn't normally consider. And even if you have a certified aircraft, there are things that you can print and install on your aircraft, even if it's certified. Again, you still have these decision points to make. For instance, how hot is it going to get? Is it a structure? Are there stress points for it? Does it have to be strong? Is it going to be exposed to 100 low lead, or is it exposed to oil, or a combination thereof? How strong do you want it to be? Does it have to be strong? So these are all decision points that you have to make so that you can choose the filaments. There's more filaments available to purchase than what's on this chart, but the basics are the ones that I'll really talk about is PETG. That one has a lot of great characteristics, but of course everything has its limitations. It's also relatively inexpensive comparatively to all of the others. What it's not good for is a lot of strength. So, but there's ABS and ASA are effectively both the same. They're great for temperature. So PETG is not good for temperature. For instance, if you're going to print something and you want to put it in your car, and the sun is going to shine on it, it's going to melt. Well, it's not going to melt. It's not going to melt like candle wax, but it's going to deform based on gravity. Okay. So, and now, let's see. Two identical parts. One is heat deformed.
One looks much cooler, yeah.
And the other one is a high temperature filament. So, but that was not done by the sun. I'm just exposing heat deformation. So, and then there's other materials depending on where you want to put it. For instance, so this one here, this is PETG, all right? And this was sitting on top of my engine. Well, the engine was, and as long as I was flying, this was fine. What happened was that when I shut down and it sat on the ramp, that's when this happened. So this one is made out of ABS or ASA, and this one can handle the tolerance, the heat under the cowl. So if you look at a piece of plastic under the hood of your car, you'll see it's all made of ABS. They're all injection molded, but this is 3D printed, but it's the same material. So it's able to handle the temperature, the ambient temperature. So, but if you wanted to have something in contact with your engine, you need something that handles a much higher temperature. And that temp, we'll get over here. Let's see, on the list. Here we go. So we get into some carbon fiber injected components, and let's see, we're looking at the PA. PA in this world is actually a nylon. So, and I don't, let's see. I don't have the high temperature with me. But I have the strong. So this is a carbon fiber reinforced nylon. And this is for structural components. It replaces this. So I'll pass this around. Now this pedal, it's a rudder pedal for the Velocity, and I have them installed on mine. The question is, everybody asks me, this is made of plastic. How strong is it? Well, nobody has ever tested rudder pedals for strength because they're made of metal. They just assume they're strong enough. Well, the Air Force actually, with a lot of research, Air Force has actually tested rudder pedals for their F-16s. And they only tested them to 300 pounds. Well, that means that in order to load these pedals, an individual has to apply 600 pounds of pressure to the tops of the pedals. This is being brakes. Rudders don't need that much. These are for the brakes. Okay. Number one is that the seat in a plane is not going to handle 600 pounds of pressure because of little aluminum hinges. But I tested it, the rudder pedal to 300 pounds. It was successful after breaking a bunch of them. And then the final test when I'm unloading them, and I've got a YouTube video if you want to take a look, as I reach down to start unloading the weights, my workbench collapsed. So the pedal survived. And obviously, as you can tell, the weight difference is substantial. So that pedal handles 300 pounds of pressure at the top of it. So with those 3 mounting bolts that are in place. So, but that's a carbon fiber reinforced nylon, and it shows that if it's printed correctly, it will handle a structural item. Okay, so here is the same material, and it's a wrench. So this one, now sometimes you need a wrench you have to be able to travel with because it's a unique size, and this is a unique size. Not many people have a nut of that size, and I have a full-size steel wrench. It's 20 inches long and it weighs 3 pounds. You don't want to travel with that, but it's on the fork of the nose gear, and you have to check the torque so that you don't get a shimmy. So having something that's lightweight that fits in, and that the reason for the notches on that is I put a pipe on it so I could load test it and to see if it was strong enough. And yes, it's more than strong enough because it only needs 12 foot-pounds of force on that nut. But I also made that so that it comes apart. So on the retract gear, there's insufficient clearance to put that on between to clear the tire. So I actually made a split wrench so that you could assemble it after getting it past the tire, and it's still strong enough even though it comes apart. So now the question is, let's go back to the engine, and how hot does that spot get? And there are tools available to us, and here's some tape. And this is there's 5 pieces of tape. It's a single-use temperature gauge. And you can buy these easy enough, and I'll pass them around. And they come in different ranges. So what you do is you tape this to the area that you want to put a part in. And then you go fly, or whatever the situation is. And then when this turns black, it tells you that it has reached that temperature. So I printed a spinner for my Velocity, and this is the cone.
What'd you make that out of?
This one is made of PETG. The spinner itself on the back of the Velocity, let's see if I have that here. That's my Velocity, and on the back of it is the spinner. And the back side of it, that's the spinner.
I can't record the screen at the same time as this.
No, you don't have to.
Okay.
Like that. So on the back side of that spinner, everybody wanted to know what the temperature was. Well, I put a piece of that tape on the back side of it, and now I've got 21 hours on that spinner in flight, and it has not recorded a the lowest temperature. So what's interesting is that just inside the cowl, I put another piece, and whether it was a connecting rod to it or the ambient temperature 2 inches in, it deformed the plastic from temperature. So just having that air gap and the fact that it's spinning, it has not exceeded what 135 or 140 degrees that temperature tape is about. So you have that as an option to determine if it's going to get hot enough. So, and to give you an idea, here are a few items. I printed this out of the ABS material, so it's a high temperature, just like under the hood of your car. This is a mount for my fuel pump. So this comes apart. It's really quite interesting. It has a locking pin. It slides apart. So this gets bolted to the firewall. And then this slides down on top of it. The pin goes in and locks it down. And I'm using a paper clip in this case, but of course you'd use a cotter pin, right? So, but the idea is that it makes it simple to take that pump off without having to disassemble everything. It also makes it a lot easier to put it together. And it turns out, because it's 3D printed, the line for this hose clamp inside is actually curved, so I'm not stressing that clamp around. Here's another unique piece. How many people are familiar with the Adele clamp? The Adele clamp is a stainless steel thing with a hose. Don't worry about that. So almost back. It's designed for hose and wire management of under your engine or around the engine. So they're a real pain to use. In fact, there's a tool that will help you to compress that to put the bolt through it. Because it's spring loaded, it really needs 3 hands to assemble this thing. So I made a replacement for the Adele clamp, which is much easier to use. And again, I have 10 of these mounted underneath my engine, and it's handling the temperature just fine. So this has areas for zip ties to attach to. And so the zip ties are not as strong as that device, and I've load tested it to 18 pounds or so. The zip ties break first. So, and it goes on very simply. So remember that hose and wire management is about keeping things from flopping around, not so much about trying to make it strong. So the Adele clamps are overkill because they're stainless steel and they're a lot harder. So really, do you need them? That's the big question. These work out just fine. So here's a tool. So let me go back to the spinner for a moment. Everything has to be tested, and you would be amazed at the amount of force that your propeller is experiencing. And the spinner is no different. It's just not spinning at the same rotational speeds, right? So we go to 2,700 RPM, the blade tips are at almost supersonic, but the center core is not. But it's still experiencing the same amount of stresses. So I have a shopsmith, if some of you are familiar with that, basically a lathe or a table saw. Think of a table saw motor. I print the spinner and I mount it on the table saw motor and I spin it to 2,800 RPM. Well, let me tell you how many I have exploded, not just broken, but exploded when it gets to that, and it will throw those pieces more than 100 feet. So, but this one is doing just fine. It's got 20 hours on it now.
What's different about this one than the others?
Well, you're going through a series of design changes as it comes apart. You look at at what speed it came apart at, and you look at how it fractured, and whether or not it needs to be strengthened, stiffened. Interesting enough, as I started, this is a 4-blade propeller. A 4-blade propeller spinner. The design work was done very quickly, and I didn't break but a few of them. When I shifted and did a 3-blade propeller, I broke a lot more because the energy is not as balanced in a 3-blade as is a 4-blade, and the distance from opening to opening is actually larger. So what was happening is it did fine up to about 2,500 RPM. When I got past that, it would start to whistle and then literally come apart in 1,000 pieces, not big pieces, just lots of, because now it just hit that point where it just couldn't hold itself together any longer. So I was able to work through that and fix it, and the 3-blade is able to sustain a 2,800 RPM spin at this point. So, but and that's the cone. They're a little bit different in size, but it works out pretty well. What's nice about the 3D printed one is that it's fewer parts, and it weighs a little bit less than what's there. So, okay, so here's another example. This is a bearing greasing tool. So you can take your wheel bearings, you pack it with grease, you put it into, and then you use the plunger and you squeeze it through, and it forces the grease through the bearing. So, but these parts, this was on the Velocity, the cooling air for the engine comes across the roof. Notoriously, it's a problem for cooling the Velocity engines. This is an IO 550 Continental engine. So these are turning vanes. So this one was designed to mount to the top of the oil cooler, as it was an experiment, of course. So, and it actually mounted in this position, so the air is coming in at this angle, and this is grabbing, this is along the top of the cowl, and then it's directing it down to number 1 cylinder, number 1 and number 2. And it was very successful. Now what I've done is I've since taken this portion and attached it to the underside of the cowl, so now it doesn't touch the engine, and this is the only part that I have. Now it's about 2 inches wide. But with the turning vanes, I've reduced the temperature delta across my CHTs from 85, 90 degrees down to 25 degrees. So that's it. There is also a filament, and it used to be ridiculously expensive. Now it's come down in price to not terribly bad. I think it's running about $150 a kilo versus $600 a kilo. But what makes this filament unique is that it does not support combustion. It does not, in other words, if you were to make a candle holder out of PETG or any of the other filaments that I've passed around, and that candle burns down and the wick is touching the filament, it will start using that filament as wax. And it will maintain combustion and keep that candle going until it runs out of film. Well, there's a filament available that you can do that with, and when it gets down to that filament, the candle goes out because it does not support combustion. I don't know how they do that. It's kind of like saying we have fire retardant paint or whatever. There's a chemical in there. But so if you were to make an electronic component or something that is going to hold a plug or something like that, that might be a consideration that you can use. So especially on a certified plane. And I lost my screen. All right. So, so the choices when choosing filament for your plane is what temperature does it have to survive? What stresses does it have to survive? Does it have to survive exposure to oil and so on? There is if you're going to put something on your dashboard, or your instrument panel and you don't have a tinted screen, there is filament that will handle those temperatures and exposure to the sun. It's just more difficult to print. Keep in mind that while I said that you can't use PETG inside the cabin, that's not entirely true, as long as it's not exposed to direct sunlight while it's in the cabin. For instance, I have parts inside the plane, and let's see. First one. Did I grab the right one? No, wrong one. Here's a quick tour of the inside of the cabin of the Velocity. And so for instance, this pouch, this door opening, I'll call it a threshold, that's made of PETG. The mounts for the gear dump valve and the push-pull cable, that's all PETG. The thing is I have heavily tinted windows, so I'm not going to see direct sunlight. But if I didn't have tinted windows, these components could not be made of PETG.
Is that because of heat or UV exposure?
It's actually the heat. It handles UV exposure. I have PETG that I've printed around the home. It's been out in the sun, direct sun, 8 hours a day for 3 years, and it looks just like that. It does just fine. And in fact, the spinners is PETG, and that's outside. So it handles that just fine. It's when you're inside, when you get to that 140 to 150 degrees, direct sun inside your car, that's when the heat actually, or the material actually gets to above that, called the heat deflection point. So, rudder pedals. So there's, even the labels on the panel are printed. Here's an access cover that's printed. So the, it gives you the ability to improve the fit and finish of the look of the plane. So this cover is 2 pieces, it pops off, it makes it easier to take things out. Here I'm covering up an ugly bolt that's on the back side. The throttle quadrant pouch is made, and I think, no, I'm skipping over that right here, but the console here is printed. The throttle quadrant and the covers, the entire lever arm is all printed. In the past, we made all of these things out of fiberglass because that's what we knew, and it worked. Very time consuming, you have to create shapes and molds and so on, and then you have to finish it. This comes out of the printer, it's all done, right? There's nothing else to do.
How big a printer do you have?
Excuse me?
How big of a printer do you have?
I have 2 printers, a small one, relatively, it prints basically the 10-inch cube, and the other one is bigger, and it does the spinner, and that's a 14-inch cube. So I have, there's a mount here that mounts my oxygen bottle. I have a cargo net that I attach up here so that luggage in the back doesn't spill forward. The vents are printed and the lights are printed. Here's a door and a storage compartment with a slam hatch. The door and the hinge is printed. mounting point for the stool. You need a stool not to get into the back seat, but to get out. So the mounting points for all the headset jacks, that's all printed. And then you get simple things like this here. There's fuel level gauge senders. Those covers are printed as well. So everything inside the cabin is PETG. If I didn't have tinted windows, it would have to be an ABS or a PC type material. So there's the throttle quadrant, all the levers, the knobs, all the knurling is all printed, part of it. The panel is also printed, so I have raised lettering, and all the panel is overlay, and it just bolts down. So there's the other door. I put stars on it. And it's opening. So engine compartment, cabin, let's see, just about anything else that you can think of that, in fact, it's not in this video, but the other one, Velocities use differential braking to steer. It's great, but it really sucks going down the runway because you're hitting the brake to steer, and that means you're slowing down. So I developed hydraulic steering that's controlled by the rudder, and those parts that allow me to connect those pistons in place are actually printed as well. In fact, here's the bell crank that's normally installed for the rudder pedals is here, and I needed to put a piston to it and extend that arm action. So that's what this is about. The engine, by the way, I have my shroud, and I'm going to exit this. And I don't know if I have that picture. Let's see. I might. So I have a high temperature carbon fiber nylon that's rated for 381 degrees Fahrenheit. And I've used that material to create the engine shroud. So that material is in contact with the cylinders, cylinder heads, and the engine casing. And that's doing very well. Let's see. Here's a here's my air box. So this is the back side. Here's well, you can't see it, but that's my gyro. But this is the back side of the shroud, and cooling air and induction air comes in here. It goes through a cleanable filter into this box, and then through this elbow into the induction manifold. So this is high temperature nylon, and this is ABS for where it sits. And the computer allowed me to design this to ensure that I had the same open space as that 3-inch induction line. So. And then let's see. So that's the outside of the air box, and I call it the feather. You've seen the silicone red rubber that you can purchase to protect your shroud. That's printed. In fact, if you have a case on your cell phone, it's made of the same material. So it's able to handle that temperature. So I printed it with all of the rivet holes already in place so I wouldn't have to drill anything. This is just flat sheet metal.
TPU?
Yes. Yep. And let's see. Oh. And while we're here, here's the, from the back end. So I get to change the colors when, you know, I don't like the color of what I've done, so I can change that. Right now, it's white with a barber pole tip instead of the black. And this is cooling cover for the alternator, and that's ABS as well. Most of the parts for the shroud, you can't see it, but it comes down, and I profiled the cylinder heads and printed all the parts that actually touch the engine out of the high temperature nylon. And then that gets RTB down to give me a complete seal. So all of those pieces are perfect fit all the way around. And then I just have flat sheet metal to attach to those pieces. So this is not the standard velocity shroud. I'm using the cowl as my cooling, as your tractor planes typically do. The velocity, they provide a tight fitting fiberglass cover. And when you do that, you take your cowl off and the engine is completely covered. If you want to access your spark plugs or anything, you have another dozen screws to take off to get that cover off. It also makes heat management much more difficult. This has done really, really well. Aggressive climb outs and temperatures have been fabulous, fabulous. So much better than last time. So, any questions?
How do you smooth out the finished product if you want to paint it?
Well, you can paint it the way it is. The texture is very subtle. But as far as, so depending on the filament, so this does not dissolve with acetone, but the ABS material is. So this here, you could put this into a acetone vapor bath, not into the liquid, but just the vapor, and it will start to melt. And you control how long it's in there. And what happens is as it starts to melt, it'll get glossy and it will smooth itself out. Exactly. So there are different techniques, but it can be sanded. Now this one can't be sanded because this is printed with one layer. Kind of think of a phonograph in 3 dimensions. So the print head is a continuous spiral all the way up until this line, and then it stops. It can't print to a tip. So that's a separate piece that's glued inside. So, and that's part of the reason for the pattern that you see here. It's pretty good, but this is one layer thick. So, otherwise, it would have a visible seam. Right? So. Yes.
How much of an impact does color have on the heat?
I haven't seen any issues with color, but I will say that when it's exposed to the sun, the darker colors will cause it to collect heat faster and deform if it's in that environment. Although the black and the red, I've found the PETG, if it's not inside the cabin, does just fine, even though it's exposed to direct sunlight. Okay, stop the recording. So it gives you an idea of what's possible. There's a lot of parts. For the most part, 3D printed part is lighter than fiberglass, definitely lighter than any of the metals that you have. It's not for everywhere, of course. There's, certain pieces still have to be metal. But the big difference between metal, fiberglass, and plastic